In this video, we're going to discuss significant figures, also known as Sigfigs. What significant figures are is a way to tell how accurate a measurement is. So if you tell somebody that, oh, it's about 10 miles from here, well, that's not exactly 10 miles. Well, maybe it's 9.5, maybe it's 11. It's close. It's definitely not 50 miles. But when we say 10, it's just because it's a nice round number. This works for some situations, but there's others where it's a major problem. If you tell your UPS driver that you have a 10-pound package and you have 100 of them, well, that looks like 1,000 pounds, and so you get charged for 1,000 pounds of shipping. But if it's really 10.5 pounds and you have 100 of them, well, that's 1,050 pounds. You basically got 5 packages for free. And trust me, no shipping company's moving 5 packages for free. We need to know that it was a little bit heavier. Being a little bit off actually matters. Other times you might notice this. Say that you earn 21 an hour and you work for 100 hours. 21 per hour. 100 hours. So you should get $2,100. Well, if your boss comes up and gives you 2,000, you say, hey, where's my extra 100? He goes, well, you're in about 20 an hour, right? I mean, he's only off by 5%. It's pretty close, but you'd be rather upset that you're not getting that extra 100. We need to be able to accurately show the value. And so this is the idea of Sigfigs. How good is the number we're using? When you say it's 10 miles away, how good an estimate is that? Is it very loose and it could be 3 or 4 more or less? Is it really accurate because you counted the exits and you know just how far down the road it is? Well, where this comes from, we have measuring devices. And so you might have a ruler, or you might have a scale for weights, and you'll put some object on it, and you'll say, hey, here's my thing, and it is this big. Well, the idea is any device that's been manufactured by any kind of quality manufacturer has been checked against known amounts. They are very well constructed so that their scales are accurate. What this shows us is that, well, I've definitely gone all the way to the 1 centimeter mark. If we count the marks, there are 10, so each of these is 0.1 centimeters. So from here to here would be 0.1 centimeter, which means I've reached the 1.1, and I didn't quite get to the 1.2. So I definitely know that I am somewhere between 1.1 and 1.2. I'm more than 1.1. I haven't yet reached 1.2. Well, what do I tell people? If I tell them it's 1.1, well, I'm a little past it. Much like the package shipping, there's a little extra weight. However, if I say it's 1.2, well, that's a little too much. Now I'm paying for more shipping than I need to. So how much in between? Well, if I look, to me that falls kind of dead center, maybe a little in front. I'm going to guess that's about 1.15. Right? It's a little bit further than 1.1, but it hasn't reached 1.2 yet. When we are trying to figure out the value from a measurement, we can't just add numbers forever. Like, there's only so many indicated on our device. When your device has markings, determine the size of the markings. So find marking units. All of ours are in 0.1. And so that is 1 spot past the decimal. And so you have a generic number, x point x. We're marked 1 past the decimal. that is actually physically shown in the device. We can be very certain, as long as we bought a good quality product, that we indeed are more than 1.1 centimeters, and that we have not reached 1.2. Humans, we do better with halves and quarters, but we can be pretty good about guessing tenths of things. And so when you write a Sigfig, when you write a number down from a measurement, the amount of numbers you get to put down, you can go one decimal place smaller than the markings are made in. So our markings were one spot past the decimal, one spot to the right. And so we get to guess one further decimal, which is why I ended up with that 5 there. I can't go any farther because this device doesn't have more accurate markings. That is as good a number as I can write down. Whatever thing I'm measuring, I can claim is 1.15 centimeters, but I cannot say it's 1.152, 1.146. I'm not allowed to go another decimal spot down. Well, when you get a number, and we write this one, 1.15 centimeters, we're going to talk in a minute about how many significant figures this shows us. Basically, if you have a number, it counts. And so I underline them here where they count. This would have 3 significant figures. 2 of them came from the device. We were very certain about the numbers in those spots. 1 of them was our guess. If I go and think about weight, let's look at the scale here. If you ever use a bathroom scale and it rotates around, well, these are, if we count, there's 10 markings in between. Each of these is 1 pound. So our markings here represent 1 pound. 1 pound. There we go. Well, if I count, I'm definitely past the 100, the 101, the 102, the 103, the 104. It's past the 105, 106, 107, but it hasn't reached the 108. So I'm somewhere between 107 and 108. And the markings tell us the ones position, just in front of the decimal. So I can keep all of those, and I can guess one smaller. So this is 107 point, and I can guess one smaller than the markings on our scale. The markings were in ones, which is the first spot in front of the decimal. So I get to guess the point ones, one spot behind the decimal. To me, that's over halfway. I'm going to guess it's about 8/10 of the way. So I think this scale is indicating 107.8 pounds. And I can't go any further. I can't say 107.85. I can't say 107.81. I have to stop just one smaller or than the markings on the device. So when you read a device, this is how you figure out how accurate your device is. There are plenty of devices where you might have a marking that says 1, 2, and 0. Well, if you have another device that says 1 and it has a lot of smaller markings, it says 2 and has a lot of smaller markings. If you use the left side, they're only marked in a full 1, which means you could only guess one smaller. So you could say that, hey, I have an object, goes from 0 to here. So that might be, 1.4-ish. But over here on this side, I go from 0 to about the same. In this case, I can see I'm slightly past the 4th marking there. So this might be 1.42. Because I have more markings on one side, if I use that side, I just can get more decimal places. I'm not allowed to say 1.42 for the left side because that's 2 spots smaller than the markings. I am allowed to say it for the right side because it's only 1 spot smaller than the markings. So the better your device, the better the number you can get out of it. Let me talk a little bit about what a Sigfig is. Talk a little bit about how we can see them on a device. How do we show them in numbers? How do you track how many significant figures there were? Because depending on your device, you'll get a different number. You want to show people how good your measurement was. If you tell your friends it's about 10 miles, and they think you're being really inaccurate, but you used the GPS, and you were able to say, no, it's exactly 10 miles between these places, down to the inch. Well, how do you show that? How do you make it clear that something is that accurate? And so there are a few rules for Sigfigs, for showing how many you have. Rule 1 is all numbers, all non-zero numbers, count. So if I have 1035, the 1 counts, the 3 counts, and the 5 counts. And I'm going to underline all our Sigfigs so we can track them. Makes it a little easier visually. We're not done yet, though, because rule 2 then comes into play. All zeros between other Sigfigs count. Well, what this means is that I have this 0 up here. I have this 0 here, and it's between the 1 and the 3, which are both significant. That 0 is significant. The idea is if you know that the parts smaller than it are accurate, you must know that 0 is also accurate. If you have a scale and it went from 10 to 11 with smaller markings, and you fell here, well, you are very certain you are at 10 and then a little bit more. And so you would end up writing this as 10.4. That 0 is significant because you do know that there's just nothing in that space. You haven't reached 11 yet, but you are definitely past the 10. So this is where rule 2 comes in. It tells us when those zeros in between numbers are important. And then rule 3. This is a double rule, so both of these must be true. All zeros right of decimal and right of a Sigfig count. So if you have 1.0350 verse 10350. So let's look at these two. Well, rule 1 says, hey, all non-zeros count. So for both of these, the 1, the 3, and the 5 count. Rule 2 says all zeros between other Sigfigs count. So right away, that 0 between the 1 and 3 counts. But rule 3 says for the remaining 0, the one over here on the right, well, both of them are right of another Sigfig. However, only the top one is also to the right of the decimal. Our top number actually has 5 significant figures, where our bottom number only has 4. The idea on the bottom number is we would have had some scale marked in 10,300 and 10,400, and we would have seen us fall right in the middle. Well, because it's marked in hundreds, we get to guess 10. So we get to guess 1 decimal smaller. So it's marked here in the hundreds. We could guess 1 smaller, which means we guessed the 50, but we weren't allowed to guess another number. However, I can't leave that out. 0 is not only used as a number, it is also used to space things. that means is if that you have, say we have 1,000 with one sig fig. Well, I can't just write 1. That looks like a single thing. I need to write those extra zeros in to show you it's 1,000. However, those zeros just aren't significant. They were used to push the other numbers further away from the decimal to show you that it was in the thousand spot. And so this is why we need rules for the zeros. They have a double use. Sometimes, like up here, they tell us that there really is nothing in that spot, that we reached a 10 but not the 11. Other times they're used just to push all the other numbers out to where they're supposed to be. So these are our 3 rules for the zeros that show up. So we'll give them a practice here in the next video.